you another. So the green theorems we talk about it is just, that was the one that I just recall the Green's theorem. Okay, that's one that we did, Green's theorem. That you're going to use it, to find those type of integral. So the integral of f dot dr is going to be on the curve C, which is going to be the boundary of a specific domain. And this integral can be defined by a double integral on the domain D, but your function is going to be, okay, it's going to be round Q, okay, round Q, round X, minus round P, round Y, okay, and the dA. This is where, of course, your function is going to be, okay, so this function is f of x comma y. In this form, your function is going to be something like pxyi plus qxyj. Okay, and this c is going to be the boundary. Okay, and the c is going to be the boundary of the domain D. That is what we did the other day. Okay, and so I just give you another example to see how I'm going to pick or how I'm going to find this. So this is going to be another one. Just get the experience how you are going to pick these domains. And we have a couple of nice ones on that practice quiz. And so we would like you to apply the Green's theorem. Okay, apply the Green's theorem. Green's theorem to evaluate this integral. Okay, would like you to evaluate the integral of over the C, and this notation sometimes means C is a closed path. Remember, you can use this one only when the domain is C is a closed curve. Okay, and this is going to be your function 3xy and dy. You want to find this integral. Of course, what is the C? Where C is the boundary of the following domain. I just wanted to see the domain is the boundary. Okay, C is the boundary of the domain is going to be, we talked about this domain before. It's a region between two circles. In this case, semicircle, we call it annular. So it's going to be the boundary of the semi. Okay, it's a semi-annular region. Okay, region D, which is bounded, region D in the upper part, in the upper half plane, of the circles, and it's going to be two circles. One of them is going to be x squared plus y squared equal to 1. This is one circle, and the other one is x squared plus y squared. Okay, this is, you can say less than equal to the point inside, and this is it. Okay, so your domain is going to be all the points between these two circles. Okay, the inside and on the circles. Then this domain would create a boundary. The boundary is going to be C. Okay, so you are qualified to use the Green's theorem. So let's get this domain to make sure we know what we are going to do. So we get these two circles. Okay, so there you are. So the smaller one, the radius 1, and the second one, the radius 2. So if this is going to be a radius 1, okay, so this is going to be one of those semicircle. Then get the other one, the radius of 2. So that's going to be 2, 2, and that's going to be 2. So this is going to be the other one. Okay, so the domain in question are going to be what? The domain in question is going to be the points in, you see, these are going to be the domain and the point on the circle. So this is going to be the domain D. Now the boundary of this domain, is that, orientation is going to be counterclockwise. This is it. So you know that you have to have a closed boundary to be able to use the Green's theorem. So the domain is going to be here. You start from this point. Okay, in this direction, you are going to go on. Then you come back here, and then you continue. Okay, you continue, and you're getting back to the where you start with. So this is going to be the domain, and the boundary of this domain is going to be the curve C. The way I just denoted. Remember, this is going to be a -2. This is going to be a -1. Then this is going to be the 1, and this is going to be the 2. So as you can see, this the boundary, the C is going to be the boundary of the D. So it makes sense to use the Green's theorem. Any question? So write the formula and then you work on it. So this is it by Green's theorem. Okay, that's it. So by Green's theorem, this is what we're going to have. So the integral in question is this, is a y² dx, okay, and the plus 3xy dy. This integral is going to be now changed to the double integral. The double integral on the domain D, okay, the domain D, area in between those two circles, and this is going to be around Q, around X minus around P, around Y. And then we decide what we are going to do about the integrations. So you have to form this one first. So this is the P and this is the Q. So identify this, okay. So the P function is going to be equal to the y². That's your P function. So you have to differentiate this one with respect to the y. So round P, round y would be 2y. That's your P function. Then your Q function is this. So your Q function is 3xy. So you have to differentiate this one with respect to the x. So round Q, round x would be 3y. Okay, then you get the difference, and you put it over here. You can find the difference, substitute, or just go ahead, do it. Okay, so the difference, if you like, so the difference between round Q, round X minus round P, round Y is going to be simply 3y minus 2y, which is equal to y. Okay, so you're just working on the y. So the integral is going to be the following. So originally, this is like the original one, P dx plus Q dy. Okay, or C, that's a Q, is equal to now the double integral over the D and just a y and dA. Now the domain is going to be that semi-angular. So you have to use, to get this integral, you have to change it to the polar form because the domain is going to be circular one. So what you have to do, as you can see over here, is between two the circles, the radius are going to be 1 and 2. So your R is going to be between, you see over here, if you want to change it to the polar form, your R is going to be between 1 and 2. Okay, 1 and 2. And your data is going to be only half a circle. Semicircle is going to be between 0 and pi. Okay, so we automatically change this one into the polar coordinates. So that's it. It's going to be integral from 0 to pi. Okay, integral from 1 to 2. 1 to 2. We have the y in polar form. We have to change it. Remember, y in polar form is r sine of the data. Sine of the data. But then there is going to be an extra, okay, an extra r. Remember that, an extra r, and then dr d data. Any question? I change it to the polar form. This is the only option that you have. So this is going to be r². You integrate r², and then you continue. So this is going to be integral from 0 to pi. Okay, 1 to 2, that's r squared. Okay, r squared first, sine of the data, dr d data. Okay, you integrate r squared, that gives you r cubed over 3. Then you're going to find it from 1 to 2. I have to go to the next page. Any question? So don't miss that extra r that you have, and automatically you know that you have to change it into the polar coordinates because of the shape of the domain. So I'm going to integrate r squared, which is going to be r cubed over 3. So this is going to be, we continue. Okay, so whatever we did is going to be equal to, we continue integral from 0 to 2 pi. We take care of the r squared, which is going to be r cubed. Okay, that gave you r cubed over 3. And then the integral going from 1 to 2. So it's going to be r from 1 to 2. And there is going to be one extra sine data and then d data. So substitutes, so it's going to be integral from 0 to 2 pi. To 2 pi, when you put the 2, that give you 8/3. Okay, minus, if you put 1, that give you 1/3. Okay, 1/3, then the sine of the data, d data. Okay, so this is going to be simply 7/3. So that would be 7/3. So I'm going to put it out. So that gives 7/3 integral from 0 to 2 pi, pi. That's it, sorry, that's pi. Semicircle, remember? Did we use 2 pi? No, pi, yeah, it's a pi. So integral of the sine of the data, d data. Integral of a sine would be negative cosine, so that gives a negative 7/3 cosine of the data going from 0 to pi. So it's going to be equal to 1 again, or the 2, just getting is, it's going to be twice of the 7/3. Okay, so this is going to be negative 7/3, negative 7/3 cosine of the pi minus cosine of the 0. Okay, that's it. Cosine of the pi is a negative 1, and this cosine is 1. So it's going to be negative 1 times negative 1. So that gives you negative 7/3 times a negative 2, which is 14/3. So the result of that integral is going to be 14. Okay, so the given integral, whatever it is, it's a y squared dx plus 3xy. Okay, 3xy dy is going to be simply over c is going to be equal to the 14/3. Okay, so this is going to be quite useful formula. Of course, you can do it directly, but if they say apply the Green's theorem, so you have to, and the best way to do it is Green's theorem, of course, to get these numbers. Okay, any question? Now, I'm going to just for a future observation, just changing this Green's theorem into the kind of, we call it vector forms, and just for one observation, and that give you a kind of a preview to the great Stokes theorem that we are going to prove maybe, or we're going to see it maybe at the end of today. Okay, so this is just a remark for observation only. So what's going to be, we're going to be observing for the last time the Green's theorem. So they call it vector forms. Vector forms of Green's theorem. This is the form that we're going to extend from for the function of 3 variables. Okay, because as is you can't do it unless you look at it from this angle. Let's see what's going to be this angle. We just in order to get to the vector form, you need this observation. Okay, just bring you something from just reviewing something from the past and prepare you for the end of this chapter or these sections. Now let's go back and have another look to see how we can change that Green's theorem to vector form. Suppose you know that in Green, your vector field is going to be a vector field in the plane. Okay, it's not going to be in a space. So this is going to be, these are two variables. Okay, P of X, Y times I plus Q of X, Y times J, or in short, as usual, we write the F equal to the P times I plus Q times J. We understand what we are talking about. Okay, suppose this is going to be a vector field in R2, is going to be a vector field in R2. Okay, in R2, and then we know that the Green's theorem tell us what? The Green's theorem tell you that this is it. So if you want to find the F dot dr, or look at this one, F dot dr over C, now it's going to be the same as PDX plus Q dy, okay, again over C. So what I'm going to do, I'm going to simplify this one a little bit, or this one, to make it a vector form, if you like. So let's find out. You see, since I want to do it in three-dimensional, if you like, so what can I do is I can imagine that this is a PQ and the next one is 0, for example. If I get 0 times K, so I'm not going to lose anything. Okay, so what I'm going to do, so I'm going to suppose this is what would happen actually in future. So in this part, I can have the P and I can have a Q. If I want to extend this one three-dimensional, I can take the third function to be 0. Okay, this is one. Then, since it's a function of three variables, then I can find, remember the curl of a vector field? What was the curl of the F? This is where I told you that you are going to use the curl at the end. So what was the curl? Remember the curl was, it's going to be differentiation operator del cross F. That was the definition of a curl, which is, it's a cross product. So if you want to find it, if you wanted to find it, it's going to be a determinant of the matrix. Okay, on the first row, we are going to have the I, J, K. Okay, that's one. In the second part, we're going to have the row partial derivative with respect to the X, partial derivative with respect to the, okay, Y, and the partial derivative with respect to the Z. And then you put your functions, which are going to be P, Q, and 0. Okay, so it's a curl of a kind of function, a vector field in R2. Let's find out. We want to get the determinant of this matrix. It's going to be equal to the I times. Okay, what is that? It's going to be I times, you cross these two out. So cross multiply differential partial derivative of 0, which is 0, minus partial derivative of Q respect to the Z. So it's going to be around Q. Then I substitute, of course, this would be 0 too. So it's going to be the first part. It's minus J. So eliminate the first row, second column. So this would be the partial derivative of 0, which is 0. Okay, minus the partial derivative of P respect to the Z. P respect to the Z. Of course, this is also 0 because P is a function of two variables. And the last part, you are going to have a K times. You eliminate these two, so that give you what? Okay, you eliminate the first row and the last one, so that give you a partial derivative of Q respect to the X. Okay, minus the partial derivative of P respect to the Y. Okay, but you know that in this case, Q is a function of two variables. There is no Z, so this is 0. P is a function of two variables, so there is no Z, that is 0. So the only thing that we get that, okay, we get that last part. So this means the curl of this function vector field in two-dimensional or in R2 is going to be simply what? It's going to be the K, which is a unit vector, remember? It's going to be the K times this expression that you know that this is part of the Green's theorem. Round X, that give you round P around Y. Okay, so this is what I'm going to get. Now what I would like to do, I would like to get rid of this K. So what I do, I multiply both sides as a dot product, of course, because they're all vectors, but I multiply it a kind of a dot product times K. So that would be change into what? So this is going to be a curl of F dot K, okay, equal to, remember this is a scalar, so I can move this one up and down, okay, switch it. So I'm going to multiply the K by K here, dot K, okay, then this scalar part, which is round Q round X minus round P round Y. Okay, but remember K dot K is just what? K dot K is just the norm of the K squared, and K is a unit vector. So this is equal to 1. So this would be 1. This would be 1, and I arrive at this formula. Curl of, there's a curl. Curl of F dot K is equal to what? Is equal to the round Q, round X, minus round P, round Y. You see? So if you go back to the statement of the Green's theorem, this is it. The Green's theorem will tell you that the term to the right of the Green theorem is this double integral of this expression. So instead of this expression, you can use this one. So that gives you a kind of a vector form. So I'm going to go to the next page and make it official. Okay, so it's like integrating both sides, if you like. If you get a double integral of both sides on the kind of domain D, so this is going to be your result. So what is the Green's theorem again? You see, so by Green's theorem again, but in the vector by Green's theorem, this is what we're going to have. Green's theorem. If you want to find the integral of the f dot dr over c, okay, which is the same as p dx plus q dy. Remember, this was equal to what? It was equal to the double integral over d of the round q round y minus round x times the round p round y. Okay, dA. Now substitute this one by the one that we did. You see, previously we proved that this is what? This is curl of the f dot k. So that gives you this conclusion that integral of the f dot dr over c, of course when c is closed, is simply equal to the double integral on the d of what? Of this expression, curl of f dot k dA. You see, this is called vector form of the, okay, this is called vector form of Green's theorem. Okay, Green's theorem. Okay, so what we are interested in, we are going to do this one at the end of today, maybe. At the end of today, we are going to create a similar formula. But we have to, we have to adjust the integrations. We do it, of course, we do it for the function. Our function is not going to be, this is a vector field in two-dimensional, in R2 only. If you want to do it in R3, you can do it. You can do it. We are going to have a similar formula for the R3, but this notion of the integral would be changed because you can't do this one. Because if you have a function of 3 variables, then this is a kind of a double integral. It's not going to be possible, but we switch it. We switch this integral into a new one, and then we create exactly the same formula. So the result is going to be called a Stokes theorem. So this result that you got so far is just the Stokes theorem. This is going to be kind of, because the Stokes theorem is more general than the Stokes theorem. Of course, in R2. It's just a preview of what we are going to plan and what we're going to do it. Okay, so everything I did is true. I can do it, but if the vector field is going to be in R2. So if the vector field is going to be in R3, you know that the Green's theorem can apply only in two-dimensional. But we are going to exactly prove this one, and that would be named as a Stokes theorem. So if you prove a Stokes theorem is more general than the Green's theorem. So you prove the Stokes theorem for the vector fields in R3, so automatically that would satisfy also the Green's theorem. But there is a catch. The catch is this integral. This double integral that you put over here. And when you go to the vector field in R3, you have to replace it by something else. And that something else is going to be the topics of our consideration today. Any question? So keep in mind this one, and at the end of the day, you will see that we get it. And that's the case one. That's also interesting, really, for R2, R3. If you are going to be a math major, we extend this one for the n-dimensional. We can do it for the function of n variables, but you have to, you have to justify everything. There is a course, we call it mathematical analysis. Usually, in the at the undergraduate level, we don't go with the, sometimes they go with the Stokes theorem for n-dimensional or the math major. Sometimes they discuss it in the graduate level, but it can be done in undergraduate, okay? But not, of course, for calculus 3. Okay, so that gives you the target. We are not going to wait. We are not going to stop here. We continue, but you have to take care of, how we're going to pick those domain boundaries, okay, simply connected, etc. Okay, so I set the target. This is my target for the end of the course. So how are we going to do it? In order to do it, we have to introduce the new type of integrations, okay? So this new integral is going to be called surface integral. Remember the surface? What is the surface? Surface is a graph of a function of, a function of several variables. You can have surfaces in R2, or you can have surfaces in R3. So we have some famous surfaces. You see, we have cylinders. We have we have spheres. All those, that we listed for you: paraboloid, hyperboloid, etc. They are all surfaces. So what we're going to do, we are going to see how we're going to integrate. In this case, we integrate along a curve. You see, that was a curve. That was a curve, a plane curve. Now we are going to do it. Eventually, we are going to take the integral along a surface. So that's why we call it surface integral. Okay. Now, you may say, oh, how are we going to use it? Quite a lot. Today, without the surface integral, you can't do anything. If you are going to come to science major, okay, or engineering. So the things are going to be, so let me just start defining it. But mostly the interpretation for the integrals that we did so far, remember, function of one variable, interpretation is the area under the curve. You can have a double integral or triple integrals. The interpretations are going to be volumes mostly. But interpretation for the line integrals, remember, interpretation of line integrals, we use the line integral in order to what? In order to define the work. So we use it in physics. So we use it on those, special fields that we have, velocity fields, gravitational fields, those conservative one. Now, how are we going to use this one? This new one. This new surface integral is going to be used in part of physics. They call it, we call it fluid flow or fluid dynamic. I think that's the expression. Or the way we are going to do it is you have a surface. Then what you can do, you can find the a kind of rate of fluid flow, okay, along a surface. If you want to find that one in physics, you have to go through the surface integral. That's the one. And the other part is you can use it for computer graphing, digital graphing, whatever you see in everyday life today, they are all coming from the surface integral, okay? Just start talking about it and I'll give you some other examples, okay? So that gives you the motivation that is quite interesting one. Sometimes in calculus 3, when we teach or, when they teach, they won't get to this one surface integral, which is very bad because the purpose for application in science is this one, okay? So it's not difficult. It's new and it's rich really. Okay, give you enough motivation to pay attention to this one, and this is it. We have to design it first. You see, as we design the other ones, how we did design the other one. Remember when we integrate line integral, you do it along the curve. So you have to have the equation of a curve. Remember the equation of the curve, see? What type of equation we use? We use parametric equation, remember? R of t. So in order to be able to deal with the surfaces, you have to have the surfaces, but you would like to have a surfaces in parametric form. So if you have the sphere, very nice. What's the equation of the sphere? X squared plus y squared plus z squared equal to the 16. But this is a kind of rectangular form. It's not going to be good for you when you want to deal with it. Because if you want to graph it, you have to find the z. If you want to solve for z, you have two hemispheres, top, bottom. Yes, we can do the top and the bottom. But when things getting more precise, you're going to lose something. So what we're going to do is, first thing is, how are we going to parameterize a surface? Or we are going to talk about the so-called parametric surfaces. Okay, that's the key to this argument. So different expression that they use, your book, they call it surface, they call it parameterize, parameterized surfaces. But the better expression really is parametric surfaces. Parametric surfaces. That's better. Means this is a surface, it's given to you by what? By parametric equations. Okay, they're all the same. Parametric surfaces. That's a better expression to remember. Or if you like, I can give another one. It's the same as parametric equations of a surface. Parametric equation or equations of a surface. That's the key to our argument. Okay. So let's remind you what's the origin of this argument. You did it before, but you did for one variable. Okay, so let's recall what we did. There you are. Where did you see this parametric equation? You can find a good pen to write it down. And there you are. So let's recall. You do it step by step. The construction is very important. Okay, recall that the parametric equation, parametric equation, the parametric equation of a curve C. Remember in R3, parametric equation of a curve C in R3 is what? Just a vector function. Is defined by, what is the definition? R of t equal to x of t, y of t, z of t. Okay, that was the case where For example, T was between A and the B. That is a parametric equation of a curve. Your function is a function of one variable. But if you have a surface, if you have a surface is given to you, then with the one variable, you're not going to be good. So what we're going to do in that case, you are going, because in the case of the surfaces, you have the X, Y, Z. Okay, so Z is going to be a function of X and Y. So remember when you do this, we keep one of them, we keep the X and we write the Y in terms of the X. But you have the Z in terms of the X and the Y. So if you want to give a parametric equation for a curve or for a surface, you need two variables, two parameters. Okay, so this is going to be the extension. The extension is if a surface equation, you know that the surface is going to be the graph of a function of two or three variables. If a surface S is the uppercase S is given, okay, given, then parametric equations, then the parametric, or this, I'm not going to use this expression, parametrization. If it's given, then the parametric equation, parametric equations of the surface is given by, okay, is given by, or is denoted by, is defined by, you see, exactly similar to this one. I'm going to use the R, but I need two parameters. I cannot do it with one. So instead of the T, I invent something like a U and a V. You can call it anything else you like. It's a standard. So R of UV, same thing. Is going to be what? Is going to be X of UV, Y of UV, Z of UV. Okay, so this X and the Y and the Z are all functions of two variables. These UV are going to be your parameter this time, okay, where U and V are going to be, U and V are going to be parametric variables. Parametric variables. Okay, this is the parametric equation of a surface that's given to me. So if you give me a sphere, I ask for the parametric equation of the sphere. A sphere is easy. What is parametric equation of the sphere? Parametric equation of a sphere is a sphere in spherical coordinates. That's going to be a problem. Let me just finish this one and I'll give you example. Okay, so this is going to be the equation we're going to deal with. So for example, if something is straightforward, sometimes, most of the time, the equation would be given to you directly. So if the surface is given by, so you are going to be given by the parametric form, not those coordinate ones or rectangular form. So if the surface is given to you by this equation, R of U comma V equal to, if they give you U plus V, that's the first component, then give you U cubed minus V, that's the second one. And the third one is going to be V cubed minus U. You see that's going to be one. So these are going to be like, this is going to be like your X, and this is going to be your Y, and this is going to be your Z. If you think about your equation of a surface in XYZ format. Okay, so if this is going to be the case, then the surface consists of then the surface. The surface S, if you like, consists of a collection of points. You know that it's going to be it's a graph, consists of all points, the points, okay, all points, if you like, X, Y, Z in R3, okay, X, Y, Z in R3, such that, okay, such that X is equal to the U plus V, Y is equal to the U cube minus V, and Z is equal to the V cube minus U. So this means if you pick different numbers for the U and the V, you are going to have different points. There is no restriction over here. You see, you can use the domain is going to be all real numbers for the U and the V, of course, okay? So if you pick any numbers, so then the surface consists of torsions R3 such that this is going to be the case. Of course, U and the V are real numbers. So I can say that for all points in points U, V in R2. So if you pick any two numbers as U and the V, that two numbers give you 1 point in R3. So it's a kind of this parametric equation, if you like, it's going to be a function. This is going to be a function that take any point from R2 into the R3. You see, if you pick 2 points here, so if you want to think about it in a geometrical format, this means in the domain of this function, the domain is going to be in R2. This is going to be the domain. So you are going to have this is going to be U and the V, if you like. So you are going to a point is given to you. You transfer these 2 points in a vector in 3-dimensional. You say that's going to be the X, Y, and Z over here. So if you pick a point here, if you pick a point like a U and the V, you see this is going to be a point. So this is going to be the U and this is going to be the V. Then this point would be transformed into a vector here. So that gives a vector. Okay, that gives you the vector, and your vector is going to be what? Is going to be R of U and V as a vector. So each point would be a tips of this vector that you can over here. So if you pick more points here, let's see, if you pick more points, if you make you get a collection of points, if you like. So that collection of points, if you like, if this is going to be the region that we're going to extend it. So this would move in different places and eventually give you a surface here. Okay, so by changing the U and the V, so you can get a image of the surface here. So that is going to be the parametric format that you're going to have. Any question? So you use quite a lot that give you a better view of your graph that you're going to have. Parametric equations is used in computer science for computer graphing. So one main application is computer graphing. You see, if you graph by point, if you have this parametric one, your graph is going to be more precise, ideal, because you are going to collect all the points rather than using a different formats that you're going to have. So it uses computer graphing. And the other part is if you look at these movies, animation film movies, the Walt Disney one, okay, all of them, they use this type of computer graphing. They all be just using the parametric form of the surfaces rather than the other part. If you are a computer science major, you are going to do quite a lot of this, or maybe interested in. So just search it with your device. There was one that I would like you to see it. We can find it. The result of that computer imaging graphing part. I just make a note that I explain it. You see, look at this one. In the book that you have in your college, you're just doing calculus 3 from the Larsen. But I do it at the university, we do it at with the Stuart. So that's calculus on several variables of the Stuart. Look at these two images that you have. You see, this is the image of the sphere by a computer. So the one to the left, you know that this is the unit sphere, x squared plus y squared plus z squared equal to 1. If you want to do it using the x, y, z, you know that usually we solve for z. When you solve for z, that give you two hemispheres. The hemisphere on the top and the bottom one, because the z would be a square root of, you know, that positive negative 1 minus x squared minus y squared. So you graph each hemisphere, then you connect them together to get the result. So if you do it kind of in that format, your image, there's going to be something, you know, when you connect these two together, let's see, look at this one. So these are not going to be such a clear and good one. But if you do the same surface, but parametrize it, use the parametric equation of the sphere. Parametric equation of the sphere, we'll see it in a minute. It's just we're just using the spherical coordinates. Spherical coordinate, you know that the x is going to be what? X is going to be r cosine of the data, sine of the power rho, of course. And then the computer would do it point by point, and that would be the result of your result. As you can see, the second one is much nicer than the first part. So that's how they are going to use it in computer graphing. And the one that the animation one, there is something that over here, I can find it. Just there was an interview on TV that I heard about this movie as well. Okay, let me just because I teach from this book, so I know some of the interesting argument. Just this is just the title. You should look at this one. This is famous animation movie by Walt Disney. Okay, it's the this is scene from the ants. Princess Bella is about to try something. You know, this is the one. And she tried to, you know, to rescue. This image that you get over here, they are all images done by the by the parametric equations of the curves that we're going to have. And for the case over here, they're just using the surface integral that we're going to talk about it. In case of the surface integral, I talk about that the surface integral can be used in a fluid dynamic, if you like, or fluid flow. And in that case, that give you that give you the rate of the flow or the speed of the flow towards the surface. So this is all they do when they, you know, we do those movies. And there is a nice quote from somebody regarding this movie that, you know, that the Walt Disney case, there are lots of interview. They talk about that they do it by using a very good programmer, computer science, and of course, an expert from calculus. And this is a quote from the producer of the movie. He said that I wish I had paid more attention in calculus class when we were studying parametric surfaces, because, you know, you see that the parametric surfaces are going to be used in order to make those all the animation that we have. Okay, if you are interested in organic computer science measure, you can search it for yourself, and then you just pay attention, because these are the, you know, it's a very handy application. Of course, you can get to more when we get the surface integral. Okay, so that is the idea. So what's your job? Your job, of course, is the equation. We are going to have two sets of equation in this section. The sets that the parametric equation would be given to directly. But there are going to be other type that the equation would be given to you in rectangular coordinates. Okay, then you have to change it. You know, the X, Y, Z, as you can see over here, the parametric one give you a better graph. So we have to practice on that. And there are some very popular cases. So I'm going to list those, the one that we're going to use. Okay, any question? So let's get the example to see how you are going to how we're going to change from those rectangular one into the, okay, into this format. For example, this is, I just list the popular one that we need. So we'd like to find the, okay, find the parametric equation, parametric or parameterization, they are all the same. Okay, find a parameterization just using this expression. So a parameterization means a parametric equation. Parameterization of a cylinder for the cylinder. Cylinder is x squared plus y squared equal to 1. You know that in two-dimensional, it's a circle, but we are going to consider in three-dimensional. In three-dimensional, this is going to be a circular cylinder. And so we want to, again, you see with this format, you may not be very much familiar or precise if you want to work with it. So you want to change to the parameterization. For this type of problems with the two variables, you can use, of course, cylindrical coordinate to parameterize this one. You see, the solution is going to be 1 or V. One can use the cylindrical, okay, cylindrical coordinates. So the cylindrical coordinate, remember, in the cylindrical coordinate, in two-dimensional is a polar coordinate and a fixed z. In the polar coordinate, you are going to have two parameters. One of them is data, the other one is going to be the r. Okay, and this is it. So a z is fixed in that case. So the parametric equation is going to be this one. And remember, x is equal to the r cosine of the data. Okay, and the y is equal to the r sine of the data. And the z is fixed. Okay, that's the case that you have. Oh, in this case, you have a unit circle, so r is equal to 1. Okay, so r is equal to 1. So we get your x to be cosine of data. Your y would be sine of the data. Okay, and z is z. So you can parameterize it using two variables. Variables going to be data and z. So the parameterization is going to be, you have r of data and z, which is going to be, that's it. Your x is cosine of the data. Your y is sine of the data. And your z is free, you see. Then you have to tell us that the data, of course, is between 0 and 2 pi, and the z is free. Z is between negative infinity and positive infinity. You see, this is a parametric equation of a cylinder, because cylinder is a surface. Okay, so this is the parametric equation of the cylinder. See, this is the way you are going to operate to get these numbers. You know, after a while, we want to get the experience. You have a various example to see how we're going to change it, switch it. Any question? So that would be for the cylinder. The most famous one, of course, is the sphere. Sphere is clear. Again, to get to know these. The one that we are going to choose, you will see in a minute. It's straightforward. So the next one, how we're going to parameterize the sphere. I've already talked about it. Okay, this is it. So you may ask, find the parametric equation or parametrization. Parametrization. It's the one that we use for graphing, okay? Or for the sphere, a sphere of radius 2, of radius 2. Okay, you know the equation in XY coordinates. Solution. So the original equation is what? Note that in this case, your equation is x squared plus y squared plus z squared equal to 4. And this is the equation, is the equation of a surface. The equation of the, of the surface is in this case a sphere. Surface, let's say S, a sphere. But you want to change it to the, okay, like the one that I show you. You want to have a better view. So we want to change it into the parametric form. Again, you need two variables to be able to do it. But for the sphere, because you have this equation, for the sphere, you can use, okay, spherical coordinates. So one can use or apply the spherical coordinates. The spherical coordinate, spherical coordinates. Of course, with, in a spherical coordinate, you have the rho, with the rho equal to 2. Because that, that this is rho square equal to 4 is going to be 2. So remember the spherical coordinate is this one. You have the x. X is equal to what? The rho cosine of the theta times the sine of the phi. You have the rho, so that would be 2 cosine of the theta sine of the phi. So this is how you parameterize the x. And using two variables, theta and phi. Y is going to be rho sine of the theta, sine of the phi. Okay, and your rho is 2, so it's going to be 2 sine of the theta, sine of the phi. Okay, so it's going to be the case. And remember the z is equal to the rho cosine of the phi. So this is going to be equal to the 2 cosine of the phi. That's it. So you can, you can write on the parametric form using two parameters. Your parameters are going to be theta and phi. So this is your equation. R of theta and phi is going to be, this is it. Your x would be 2 cosine of the theta sine of the phi. Your y would be 2 sine of the theta sine of the phi. And your z is 2 cosine of the phi. And of course, you have to tell us the domain where your data is going to be between 0 and 2 pi, and your phi is going to be between 0 and pi. So that's going to be one, because this is going to be domain for your function. You see, if you like the domain of your function, the domain is going to be, you get a closed interval of 0 and 2 pi for the data cross the closed interval of 0 and pi for the pi. That would be enough, but if you want to write down different symbols, this is going to be the case. Okay, so we can, we can quickly get the parameterization of the sphere. Any question? So that gives the idea that the way you are going to operate with your parametric form. And this, the next one is the one that you are going to use most of the time. You see, these form, especially this one, we didn't have the z. And if you want to find the z, you have to use the positive negative. But in most of the time, because we are going to check this idea of the surface integral with the scalar function first, then we go to the vector field. If you have a scalar function, this can be done quickly. So I'm going to show you. Most of the time, you are going to use this last one. So pay attention again to the last one, or the last example that we have. You see example. A scalar function, okay, is going to be, again, you want to find the parameterization. Find a parameterization. Parameterization of this paraboloid. This type of form are popular. Okay, it's a paraboloid. An equation given by this is it. You have f of x comma y is equal to the x squared plus y squared. Okay, you know that this is, or if you like, z equal to the x squared plus y squared. This is the case. Because even it's the function is explicitly is given to you, it's very easy to parameterize this one, because you have the x, y, and z, okay, over here for the surface. So what you can do is you need to use two parameters. Okay, so you have three variables over here: z, x, y. So the parameter for this one, you can use the x and the y as your parameter, and the z is given to you in terms of the x and the y. So quickly you can parameterize it. You see, this is like the one that we did for the function of one variable. You see, if you have y equal to the x squared, you can x to be t, so we get t and t squared. This is one way to do it. Or you can go with the x and x squared. It's the same for this one. If you like, you can take the x to be u, y to be v, then we get u, v, what is z? U squared plus v squared. But sometimes it's going to be useful for you to check it in terms of text. So I give you two versions of these, okay, solution. So one way to do it is, this is it. And note that, again, we emphasize that the surface z equal to, even if it's given to in this form, you have to change it to the z. Z equal to the x squared plus y squared is the equation of the surface. Okay, is the equation of the surface that you want to parameterize it. Equation of the surface. We call it the surface S. Surface S. So one way to do it quickly is this one. Note that you can use x and the y as your parameter. So r of x comma y is equal to the first parameter, you keep the x. The second parameter, you keep the y. The third one, you have to find the z. What is the z? Z is x squared plus y squared. You see, that gives you the one right away. So the parameters that you use are x and the y. Okay, so this is going to be is a parametric equation. Okay, parametric equation of S is one way to do it. And this is good to do this in terms of the x and the y, because you are going to getting involved with the integrations and you don't have to switch anything. But if you don't like it, pick any. You see, you have three variables here. You have the freedom of two here. So the freedom of two, but not the freedom for the third one, because the third one depends on the other two. If you don't like this one, this is another method. Or if you don't like it, let x and the y to be anything you like. If you don't like this notation, you can let x to be equal to the u is a free agent, okay? Y to be equal to the v, a free agent. Then your z is what? Z is x squared plus y squared. So it's going to be u squared plus v squared. okay, then your parametric equation in terms of the u and the v is going to be what? It's going to be u squared plus v squared. You see, these are going to be the what? But this would be easier to handle because you have to differentiate it. Remember, we are going to go through the integral, but it doesn't matter. So that gives you an idea. If it's going to be a scalar function, you can quickly take care of it. If the c is already given to you, the difficult for the other problem was that there was no z, or you cannot find the z. It's a kind of implicit form, so that you have to go through and So it's like the one that we did before to parameterize. Okay, any question? So now this is the domain. This is the surface that we are going to eventually integrate through this surface. Okay, reducing power. So I can give a break. We come back and we prepare for the surface integral to see what we need. So we are going to prepare everything we need, and then eventually we are going to be able to do it. If you just check the way I just used the vector, you see, look at this one. The way I changed this, and this is a k here, or the way we did it before for the, you see this k is a unit vector. It's going to be unit vector, and this is going to be kind of a normal vector, if you like. So what we're going to do, we are going to create something which is going to be eventually we call a normal vector. Let's have a break, come back. The preliminaries are the one that we have to put together, and eventually we get a nice observation. So it's at 12 o'clock, 15 minutes. We come back and there is a normal vector that we have to define. Then we put them together and we are going to be prepared to talk about the surface integral at the end. Okay, have a break and then we come back and we finish it. Okay, so we are going to continue. So what we did so far, we just define the parametric equation or show that what is, or how we're going to write a parametric equation of a given curve. Okay, so the next step is going to be we are going to define what is going to be the normal vector. We are going to be interested in finding a normal vector to to these parametric surfaces that we're going to have. Okay, so the way we are going to do it, you know that when we talk about these normal vectors, you are familiar that we start with the tangent vector. And usually the tangent vector give you the this is going to be the one, then the normal vector would be a line which is going to be perpendicular to the tangent vector. This is the way we do it for the usual function. So in this case, your parametric equation is going to be a function of two variables, r of u and v. So what we are going to do, when we get a function of two variables, remember, we can use the partial derivatives as the tangent vector. So we have a partial derivative with respect to, depending on the variables, partial with respect to the u, respect to the v. So if we consider the partial derivatives as vectors or the tangent vector, then since the normal vector should be perpendicular to those tangent vector, so what we need is we are going to consider the partial derivative with respect to the u and the v that give us two vectors. Then the third vector is the one that's going to be perpendicular to both of them. And you already got this idea that the cross product would give you a vector which is going to be perpendicular to the two given one. So we are going to use this idea to introduce this normal vector. This normal vector would give us do the job for us when you go to the integration and replacing that k that I show you. Okay, so that would be your next step, and this is your main step when you're dealing with the eventually surface integral. So what is going to be normal vector in these cases? So what is a normal? Okay, normal vector. Okay, normal vector to one of these cases, to a smooth, if you like, a smooth parametric surface. Okay, so this is going to be our plan. So let's start with one of these equations given to you. So you are going to have this equation would be given and you just do it yourself. Okay, so if r of u v, now you know what does it mean, which is going to be x of uv, y of uv, and the z of uv. Okay, if this is going to be the one, this is of course is a parametric equation, is the parametric equation of a given surface, or parametrization. Parametric equation of a given surfaces, okay, of the given surface, okay, given surface S. So this is given to you. Of course, there's going to be a domain, let's say with the domain, it's a function, so it's a great domain. With the domain, okay, with the domain D. Then a point would be given to, then you want to find that normal vector, then at the given point, then at the point, okay, at the point with the coordinate of x0, y0, z0, okay, the normal vector to the S, okay, to the surface S, okay, to the surface S is going to be given by given by, this is the normal vector. The normal vector is going to be r sub u, is a partial derivative respect to the u, cross r sub v. So the partial derivative respect to the, respect to the v. You know that those partial derivatives would be vectors, and then you consider the cross product. And the cross product, you know that the cross product of these two vectors, so this means n is perpendicular to this tangent vector ru, and it's going to be perpendicular to the rv. So in fact, it's going to be perpendicular to the, to the plane, if you like, to the plane that would be spanned by these partial derivatives vectors that we're going to have. Okay, so it's a cross product, so or remind you the formula. So the cross product, remember, n is going to be the determinant of this matrix. The first part's going to be I, J, K. Okay, and then RU. This is it. Differential respect to the U. So we're going to have a round X, round U. Okay, round Y, round U. And the round Z, round U. And then we go with the V. So it's going to be round X, round V, round Y, round V, and we go with the round Z, round V. So that would be the determinant of this matrix is going to be your, your normal vector. Okay, as I talk about it, this is important to know that. Note that this vector n is going to be, is a perpendicular to both of them, you know that, is a normal vector. Okay, it's going to be a normal vector to the tangent, okay, to the tangent plane as usual. Tangent plane is spanned by or generated by, is spanned by the tangent vector. Okay, spanned by the tangent vectors, and they are going to be, r sub u and r sub v. That's the idea of the normal vector. So the normal vector is going to be perpendicular to the plane. That plane would consist of the combination of these two vectors that we are going to have. Okay, so we usually give you one and we ask you to find it for us. Any question? Yes, so they usually ask for the normal vector and this plane. So you know that you write the equation of the plane, you need the normal vector, this is going to be your normal vector. Then you need, you need a point. The point is going to be the one that's going to be given to you, okay? So it's a straightforward problem, but you have to know that the formula for your normal vector. Okay, so this is going to be the actual example or our first problem, or the second, because the first one was parameterizing. Okay, there you are. The standard problem, find the normal vector, find the normal, find the normal vector and the equation of the plane. And the equation, the equation of the tangent, equation of the tangent plane, to the surface, given by the parametric equation. Okay, given by, so this is the surface, r of uv is equal to, so they give you 2u times cosine of the v, this is the first component, I, plus the second component is 3u sine of v times j, and the last one is going to be u squared k. Okay, so these are going, that's a u squared. Okay, of course, then you must be given a point at this point, at the point. Okay, at the point with the coordinate of 0, 6, 4. That's it. So when you find it, that would be the normal vector. You have a point and you can write the equation of the plane right away. Okay, so we go for it. The point that's given to is going to be x, y, z coordinates, since you use the u and the v here. So you need the u and the v because that would be easier to substitute quickly. So the first thing to do is just find those corresponding points for the parametric. Okay, the value for your parametric variables, if you like. So the first thing to do is this. So note that the one that's given is a point in three-dimensional x, y, z. So the x, y, z is 0, 6, 4. Okay, so if you go with the uv, so this is going to be, you see the component that you have. Okay, so if you compare it with this component that's given to you, okay, you compare it. So your x is 2u cosine of v, your y is 3u sine of the v, and the z is u squared. So put them together to guess what is going to be the u and the v. So that give you x equal to the 0. You see x equal to the 0. So this will give you 2u cosine of v equal to the 0. Okay. And then the second part is going to be y is equal to the 6. So your y is 3v sine of the v equal to the 6. And your z is equal to 4. So that gives you u squared equal to 4. Okay, so you compare this together to find the u and the v to get this true. Okay, so what we can do is we can go with this one. Okay, find the u first. So for example, if you pick the u to be equal to 2 here. Okay, if you pick u equal to 2, and then you can take care of this. Okay, from here, you get the cosine of v equal to the 0 because the u is not 0. And that would give you v equal to the pi half. Okay, you can check it with the other to make sure that I didn't take positive negative 2 because these are going to be consistent with the 2. So u with the 2 would, it satisfy this one. If you bring it here, so that is u. That's a 3u. 3u. Okay, because if you put the pi half, sine of the pi half is 1, so 3u equal to the 6 is consistent with the u equal to 2. So that's why I didn't use positive negative 2. Okay, so uv is going to be 2 and pi half. So you keep this one because you have to evaluate that normal vector at the u and the v. You don't have to go back and substitute. Okay, so now go and find it. You have to find the normal vector, which is going to be this is going to be normal vector. So I go to the next page. Any question? So find the corresponding point, and then we are going to form the normal vector n. So the normal vector is this. You see the n is equal to the ru cross rv. So this is going to be, and that's the ijk, ijk. Okay. Then ru, you differentiate respect to the u that you have. You see the function that we have is going to be differential respect to the u. So the first part was 2u cosine v. So if you check it, that give you derivative would be 2 cosine u, cosine v, the first one. The second one would be 3 sine v, and the third one would be 2u. So I differentiate the r respect to the u. If you differentiate with respect to the v, so that give you, okay, the other one, it's going to be 2u sine of the v. Okay, and you get the 3u cosine of the v, and in this part, you are going to get a 0. Okay, so I just differentiate each of those functions. For the first part, I differentiate each component with respect to the u. In the second part, I take the derivative with respect to the v. Remember, the first part was u squared, the third one. So the derivative of u squared with respect to the v would be 0. So just evaluate the determinant. So this is going to be I times, you eliminate these. So nothing here. So that gives you 2u times 3v. So it's going to be 0 minus, okay. So this is it. So it's going to be 6. It's going to be minus 6 uv cosine. 6, okay, 6 u squared cosine of v. So that's the first one, minus j times, eliminate the first row, second column. So this would be 0 again, 0 minus these two together, negative would be positive. So to make it to the positive, 2u times 2u would be 4u squared. And that gives you a sine of the v. Okay, that's first. Then we get a k times first row, first column. Now you multiply these. So that gives you 6u cosine v squared. 6u cosine square of the v minus. Okay, there's the negative to make it to the positive. So that gives you, okay, so that gives you what? That gives you 6 plus 6 is going to be 6u cosine square of the v again times k. Okay, so simplified further, that is give you the n is going to be equal to, for the first part, you are going to get the negative 6u squared cosine of the v times I. And the second part, you are going to get the negative, okay, this is it, 4u squared sine of v times j. And the last part, you see the last part, you can pull out the 6u. So the leftover is going to be cosine square of the v plus sine square of the v, which is 1. So this would be 1. So the last part is going to be plus 6u times k. See, that's going to be the case. But remember, you have to evaluate it at the point that you'll be given. So the point, we change it to the u and the v. So the point uv is, remember, it's a 2 and pi half. That's why I changed the xyz into the uv, so I'll be able to substitute here quickly. So substitute u equal to 2 cosine equal to the pi half. So this is it. So the n is going to be the first one, because of the sine of the cosine of the pi half is 0. So you won't get anything that give you 0. In the second part, you have a sine of the pi half. Sine of pi half is 1. 2 squared is going to be 4 times 4, 16. So that give you a negative 16. Okay, and the third one, 6u. 6 times 2 would be 12. So that give you 12. So this is going to be your normal vector. Any question? So, you know, it's not bad, but you have to pay attention to get through it. So we have the normal vector. So that's the normal vector. Normal vector. They ask for the normal plane. So this is going to be the case, of course, at the point P. And the point P is given to is 0, 6, 4. So you are ready to write the equation of a tangent plane. Okay, so the equation of a tangent plane, you know that in the case of the tangent plane is going to be, so you have a normal vector is a B, C, if you like. That is a 0, negative 16, and 12. And the case for the point x0, y0, z0, that's just for your information. It's going to be 0, 6, and 4. So you want to write the equation of the plane with the normal vector and the given normal vector and the point. Remember the equation is what? A times x minus x0 plus b times y minus y0 plus c times z minus z0 equal to the 0. That's a general form of the equation of the plane. Now substitute. So your A is 0. 0 times x minus x0, which is 0, plus b. B is a negative 16. Negative 16 times y minus y0, which is 6. And plus c, which is 12, times z minus z0, which is 4, equal to the 0. Okay, so this is 0, all would be canceled out. And over here, this is going to be negative 16. Okay, I want, eventually we have to simplify it. So it's going to be negative 16y plus, okay, plus 96. 96, and that would be 12z minus 48 equal to the 0. So put them together. That give you the final answer. Okay, you can simplify it. It's a negative 16y plus 12z, and the number is going to be plus again 48 equal to the 0. You can simplify it by 4, and that give you the final answer. Simplified by 4, that give you negative 4y, okay, plus 3z plus that's a 12 equal to the 0. So that give you the equation of the tangent plane. Okay, so this is tangent plane. Okay, so you have some problems in your book. I think you have one in your review. Okay, so that is the normal. Any question? No. Now let's get back to see how we're going to connect it to eventually to the integral that we are going to be interested in. Okay. And so we're going back into the special case that you're going to be interested in. A special case that we're going to be interested in is the one that, the function would be given to you. The equation of a function would be given to explicitly z equal to the, let's say, g of x, y. Since we are going to use this one most of the time, and so we are going to stay with that format, because the way we are going to do the job is the surface integral. I'm going to define it for the scalar function first. So it's going to be a kind of function of 2 variables. The domain is real numbers. And then when we're done, we're going to extend it into extend it to the vector field, as we did it for the line integral. So we're going to prepare ourselves for that scalar values function. Okay, so let's see what we need. So we're going to work on it we give you as a remark. Okay, again, they can be, talk about it more details, but we don't need it. We want to get through that so that we can get to the surface integral as quickly as possible and not to lose anything, but be able to, to get to the Stokes theorem. Now, this remark is very important for you. Okay, so this is it. So let's focus on the special function that we are going to be interested in, a scalar value function. So if it's going to be a special, so note that if your function is of this form, z equal to, let's say, g of x comma y. okay? We keep the f for the function that we are going to integrate it. So for the surface, we go with the g. So suppose this is the equation of a surface, okay? Is a given surface. Okay, I stay with the extended. This is, parametric equation of this one is easy. As we talk about it, if you love u and the v, you can change it. But I prefer to stay with the x and the y here. So the parametric equation is going to be r of x comma y. Simply x is a free agent, y is a free agent, z is g of x comma y. You see? That is going to be parametric equation. Okay, so is the parametric equation of a surface, equation of the surface. Okay, now let's find the normal vector as is. So as is, if you want to find the normal vector, so what you need, okay, so note that you need to differentiate partial derivative with respect to the parameter. So the parameter are x and the y, so the partial derivative with respect to the x is, derivative of x is 1, derivative of y respect to the x is, okay, is 0. And partial derivative of this function respect to the x, we call it g sub x. This is going to be the tangent vector, in the direction of the x. Then second parameter is y. So differentiate respect to the y. This would be 0. Okay, this would be 0 and this would be 1. And this would be g sub y. Okay. So what's going to be the normal vector? Cross them together. So we get the normal vector is going to be Rx cross Ry. Determinant of this matrix, as usual, that's going to be your I, J, K. Then the first vector is 1, 0, G sub X. The second vector is 0, 1, G sub Y. Get the determinant of this vector, of this matrix. What's going to be the determinant? This is going to be I times, eliminate the first row, first column, result 0, minus, okay, it is going to be 0, minus G sub X, okay, minus J, times, eliminate the first row, second column, so that's going to be GY minus 0, okay, plus K times 1 minus 0. Okay, it's going to be 1 minus 0. So what's going to be the conclusion? The conclusion is going to be the normal vector. You see, the normal vector in this case is going to be what? You get the Rx across Ry. And now this is going to be this vector. Look at the vector. The first component would be negative G sub X. The second component would be negative G sub Y. The third component simply would be what? Would be 1. You see? So you don't have to worry about it if you know it in advance. It's not a big deal to do it again, but if you know it in advance, you can use it. Okay, so that would be normal vector. Okay. Now, what's going to be the norm of this vector? Okay, it's a normal vector. It's not a uninormal vector. So what's going to be the norm of the n, or the norm of the Rx cross Ry? Remember, the norm is the sum, a square root of a sum of the square of those components. So it's going to be a square root of, okay, it's going to be a square of the, I write down from here. It's going to be 1 plus g sub x squared plus g sub y squared. So in that case, that would be the norm of the norm of your normal vector. Any question? Now, what we can do is we can copy the idea that we did before. Remember, we did have the area of you get a function, you have a function of one variable, then you talk about the surface area that you did. Now we can do the similar thing for these surfaces, and to prove that in that case the surface area is this one. Remember, for the surface area, we're just integrating what? Integrating the norm of the arc prime of t, or the arc length. This is the way we did it before. So we are going to introduce something very similar. That something similar is going to be the area of a surface. The area of this surface is going to be a double integral on the domain of the d. The norm of the norm kind of r prime that we did before. You can be sure that it's going to be the same as here. So it's going to be the square root of 1 plus g sub x squared and the g sub y squared, and of course differentiating, integrating respect to the y and the respect to the x. Okay, similar argument that goes with this one to get this double integral, if you like. So this is going to be, you see, this is the area of these type of surfaces. If the surface given to you by a parametric equation, then this is the way you are going to find the area of that surface. This is, of course, for the scalar function, so we can make it more general. So what we did really is just a norm of the normal vector. So we can extend it. We say that, in general, if your equation is going to be given by a parametric form, so in general, if the surface, if the surface area is given, if the surface area is given by the parametric equation, by the parametric equation, or the surface is given by the parametric equation of the form of R of U and V, then this formula would be extended to nothing new, it's exactly the same thing. So the area of a surface is going to be a double integral, on the D. This is what? This is only the norm of the normal vector. So you find the normal vector, which is the function of U and the V, and then you are going to integrate it respect to the U and the respect to the V. And you know that this is where this n of uv is simply the normal vector. Is the normal vector. So what we did really, we just give you a formula for the area of a surface, but when your surface equation is given to you by a parametric form, it's going to be a parametric form. It's going to be the same thing that you did before, but it's going to be double integral, and you get this one. But if it is going to be just a scalar function, you can use you can use this formula. So we can have both of them together, so that we'll be able, to apply it right away. So we are now in a position to introduce the surface integral for you. Integral along the given surface. So that's it. We just do it for the scalar function first. So we begin a scalar function. You gain a surface with this information. The parametric equation of a surface is given to you, so you have all the information that you need. Then what you would like to do, you would like to find a kind of an integral of the function along the surface. So This is going to be the idea. And this is the one that we use in fluid, okay, fluid flow, okay, or fluid dynamic, if you like. Okay, there you are. Surface integral. Today for a scalar function, then we extend it to the, okay, we extend it to the scalar, extend it to the vector fields. And that would be the, okay, that would be the Stokes theorem, and then we're done. So let's see surface integral. You want one of them to evaluate. There you are. If a surface is given to you, of course, with the parametric equation. If the surface okay, S is given, okay, given by the parametric equation, parametric, it may be given or you may have to find it. Equation R of U and V, and F is a function, and F is going to be a function, on the surface, on S with, okay, with continuous partial derivative, partial derivatives. You need this to be able to know to differentiate partial derivatives. Okay, partial derivatives. Then the surface integral. Surface integral of F, of the function F, okay, over the S, if you like, is going to be defined by, that's it. It's a double integral. The function is a function of three variables, X, Y, Z, but it's a scalar valued. So it's a function of three variables, but the range is numbers. Later on, we change it to the, okay, we change it into the vector fields. You know, you need to do a little bit of modifications. So that would be ds. These are all uppercase S. These are the surface. Okay, and this is going to be equal to, is equal to the double integral on the domain D, the function. Look at this one, f of, what you do, it's like the one that we did before. You have to take this double integral over this surface. When you do it over this surface, you know that the way we did it before, we did have a parametric equation of a curve. So that was f of RT. Remember, f of RT, norm of what? F of RT times norm of the R prime. Now, instead of f of RT, you have a parametric equation of a curve. Parametric equation of the curve is what? Is f of R of U comma V. You see? That will replace it with this one. Then remember, we multiply by norm of. Previously, we did have a norm of the R prime of t in the case of the line integral, when you integrate this way, along the curve. But instead of the R prime of t, we are going to have what? We have the normal vector. So it's going to be norm of the normal vector u, v, normal vector, and then, of course, du, dv. So it's a kind of extension of that integral. And you can know, if you want to prove it, you're just doing those partitioning one. You have a surface, divided into the different parts, and eventually we get this one. And instead of one sigma, you have a double sigma, if you like, to be able to get this one through. So you have a parameterization of your curve R of uv. So you have to find the normal vector, okay? You get the norm of the normal vector. So you bring this one in and the evaluation of your function, and eventually you integrate into the domain. It depends what you are going to get at the end. What type of domains do you have? And then you'll be able to, okay, to take care of it. And the domain is as usual, it's going to be from 3-dimensional, you drop it down into 2-dimensional. This domain, when you parameterize it, you see the domain, then you integrate it. Now, a special case that most of the time you are going to use is if the equation, okay, if this function is given to you explicitly, means z is solved already for x and the y. So if the equation of the, sorry, for the surface, if the equation okay, equation of the surface is given by, if the equation is given to in the, okay, in the xyz coordinate form, if it's given you by z equal to the g of xy, remember I've already get this one for you. You see that is going to be the case, that the normal vector is a square root of 1 plus g partial derivative of g respect to the x square, partial derivative of y respect to. So if this is going to be the case, then your integral is going to be this one. And this is usually be used for those scalar part. So the surface integral, okay, that is going to be the case, surface integral. So you get the same thing, double d. So f of, in this case, you have uv and r of uv, but in this case, you have xy. So you are going to fix the x, fix the y. Then instead of the z, you are going to use the function g of xy, because that's your z, you see. X, Y, Z, X, Y, Z. Z is g of xy. Then norm of the normal vector. In this case, you do have the normal of the normal vector, and that norm is a square root of 1 plus g sub x squared plus g sub y squared. Okay, so when you're done with everything over here, and this is going to be dx dy. It's the same thing, but it's nice to have it so that you are not going to be confused and you do it right away to get this surface integral. Okay, so as I talk about it, one application of the surface integral is going to be used in those fluid dynamic. If you like, from the physical point of view, the surface integral, okay, the surface integral, and this is it, f of x, y, z ds, it can be considered of the rate of, or the speed of the rate of fluid flow, if you like, in physics, if you like. When the situation is given, then you can use this one, let's say in dynamic or in physics. I'll give you one example later. But this is how they related to get these numbers. So it's going to be rate of fluid flow of the force. The force that you have is this F over here to get this one through. So again, that would take us to the application. Okay, the application for those fields, vector fields. We're going to extend it into the vector field. It's just for the scalar function at the moment. Okay, it's not difficult to find, but you must make sure that you're not going to be confused. Okay, most of the time this is in the form of the scalar valued. So you do it step by step patiently, you'll be able to find it. There is nothing complicated about it. So have your formula. This is case one, a scalar. The case two is we change it to the, okay, we change it into the vector field. If you have a vector field, you know that they are going to be vector. So instead of this product over here, this would be a vector. We drop the norm and we use the, okay, we use that kind of dot product that we're going to have. So we are going to see it. That would be the last case that we're going to consider. Okay, so I need to give you one example to make sure you know this one, and then we just finish it on Monday. Tomorrow we practice on those, you know that we practice on for your quiz. So we practice mostly on line integrals and the Green's theorems. Okay, then you get two questions from this part beside the other one. Then we can check it again on Monday. So let's see. Okay, so this is the last type of the integral that you have. So you have the, you have those double integral, triple integral, then you have a line integral, and now you have a surface integral. So you have all different types of integral, classic type of integrals that you can use in science. And the next step is going to be integral in general. Okay, then there is a course, we call it measure theory. So you have to take that course. It's a very hard course. It's advanced mathematics, of course. And then we are going to talk about the set function. A set function is a function that's defined on sets, like probability. So when the people, they say statistics is a difficult course, a statistics is not a difficult course. Probability part is difficult because that would take us to the notion of integration. Okay, the measure theory is a one big branch of mathematics. Okay, if you want to do any graduate studies, in a master program or a PhD, you have to start with a couple of courses, or at least one course in measure theory. Okay, let's have the example. There you are. We give you one on the final. If S, a curve, a parametric format of the surface would be given, and we ask you to find this integral. If S is a part of, okay, it's going to be a part of the coin X equal to square root of Y square plus Z square. You see the equation is given to you explicitly, directly. So it's good. So is the part of the coin bonded between planes. Bonded between planes X equal to the 0 and X equal to 1. Okay, if this is going to be the case, we want to evaluate this surface integral. Double integral on the surface S, and this is x squared ds. That's it. Okay. So that would be the target, to find it over here. So first thing to do, you have to check your surface. Okay, you check the surface and you find, I can write the formula for you so that you know it. You see solution is going to be, and that's it. If you want to find this double integral over, the surface S, x squared ds is going to be equal to, you see, you get the double integral on the domain of the D, the function f of what? This is the general formula that you have. Is going to be f of x, y, remember? It's going to be x, y, g of x, y. Okay, then we get the norm of n of x, y, then the dx, dy. This is the general one. But in this problem, you have a little bit of a modification. What's going to be your g? You see your g function is, so the surface. The surface S is given to in this form is going to be x equal to the y squared plus z squared. So it's a function of y and z. You see, is a function of y and z. So when you write your formula, so this is going to be the case. So you are going to have a, okay. So, this is going to be a little bit, you change it because it's going to be g of y and z. So these are going to be, okay. It's going to be kind of y, z, g of y and z. It's not important. Let's get the other part first. So this is going to be your function. Then what you have to do is you have to find that part here. That would stand for the ds, if you like. So we go with the ds, which is going to be the same as, okay, it's the same as this norm of your vector. Okay, it's again the same as the norm of the normal one, but the function is going to be function of y and z. Y and z. Remember, in this case, is equal to the 1 plus the partial of the g respect to these variables is going to be partial of the y respect to the y squared and the partial of the g respect to the z all squared. Okay. So differentiate it. So g of y and the z is going to be equal to, rewrite it. You have two problems in your book similar to this one. It's going to be 1/2. So I'm looking for, finding the normal vector. This is what I'm doing. So respect to the y. So what's going to be gy? You have to use the chain rule. It's going to be 1/2 y squared plus z squared to the negative 1/2 times the u prime derivative with respect to the y, which is a 2y. So that gives you 2y. So the 2 and 2 would cancel out. So derivative with respect to the y would be simply what? Simply y over radical y squared plus z squared. So that would be your gy. Any question? Then similarly, we find the z. Similarly, you see they change the function. It's a function of x and the y and the z. So similarly, g of z is going to be the same thing. So the top is going to be z over, let's say, the y squared plus z squared. So that's your gz and the gy. Go ahead, simplify it. You get this quantity here. So find what is going to be 1 plus gx squared, gy squared and the gc squared. So it's going to be 1 plus. If you square it, that gives you y squared over y squared plus z squared plus z squared over y squared plus z squared. Okay, so it's 1 plus, you add them together, that gives you y squared plus z squared, and that would be y squared plus z squared. It's nice. You get 1 plus 1, which is 2. Okay, so this would be equal to 2, so you get your normal vector right away. Okay, so if you take the square root, that would be the norm of the normal vector, or ds, doesn't matter, it's the same thing. So the norm of that normal vector that you have in this case is going to be y and z. Okay, this is going to be equal to the radical 2. Okay, or if you like dz, ds is radical 2, it's the same thing. Some people, they go with this one, it's easier to memorize it because this is just the ds. Differential of the surface area. Differential of the surface is the same as the norm of the, okay, normal vector. Okay, now we are ready to set up the integral. So this is the way you are going to set up the integral. In this form is easy. So you are interested in this integral. That would be x squared ds. Okay, is equal to, okay, so this is going to be the double integral. If you like, I can rewrite it again, but you don't need it. Okay, so It's going to be on the domain. So your function now is going to be, okay, the function is going to be this is the function, is going to be x, y, z again, x, y, and okay, and this is going to be x, y, the one that I did really, that's it, that's it. And the norm vector is going to be n of y and z this time, and you're integrating respect to the y and the z. Now, your function is x squared, okay? So this is it. So f of x, y, and g of x, y is going to be x squared. But the x squared is equal to what? Now remember, your x is radical y squared plus z squared. So this means your function f of x, y, g of x and the y. So you have to, evaluate it on this surface. So it's going to be simply y squared plus z squared. Okay, you evaluate it on the surface. So we go back and this is it. So the double integral on the surface of x squared ds, and we now substitute the norm d. Okay, the function is y squared plus z squared. And the normal vector, the norm is radical 2. And then you integrate in respect to the y and the z. Okay, you can pull out the radical 2. So you are going to find the radical 2, the double integral of y squared plus z squared. Okay, then the dy and the dz. Now go back to see what the restriction you have, what sort of domain do you have. And remember, the thing that you have is that, note that they give you two planes, x equal to the 0 and x equal to 1, that's a plane. And then you have the fact that the x is equal to the y squared plus z squared. So this means, so the domain of your information, okay, the domain in the two-dimensional, if you like, that you want to integrate is going to be the following. So your domain is going to be a collection of points of y and z. Okay, y and z that satisfy this condition. You see, this is x. So the condition is that is going to be x, which is the radical y squared plus z squared. Okay, this is going to be less than equal to 1. Or you can square it. So your domain is going to be a circle. It's going to be y is z, okay, and y z, and when y squared plus z squared is going to be less than equal to 1. So that the last part, the integral, are going to be evaluated on the circle. So the double integral is going to be, can be found using the polar coordinates. And so the polar coordinate of this is r is going to be equal to between 0 and 1 as usual, and your data is going to be between 0 and 2 pi. So the radical 2, the double integral of the y squared plus z squared, okay, the dy dz would be changing to radical 2, 0 to 2 pi, okay, 0 to 1 for the r. Your function is y squared plus z squared, which is going to be r squared. It's a polar coordinate, so there is an extra r. Then, of course, dr, d data. Okay, so that make it to the r cubed. So it's going to be integral from 0 to 2 pi. Okay, integral from 0 to 1, r cubed dr d data. So it's going to be radical 2, 0 to 2 pi. So integrating r cubed is going to be r to the 4th over 4 between 0 and 1, then the d data. r to the fourth between 0 and 1 would be just a quarter. So this is going to be equal to, okay, is going to be radical 2, okay, radical 2, 0 to 2 pi, just a quarter, then the data. So bring a quarter is going to be radical 2 over 4, integral from 0 to 2 pi d data. That integral is going to be data, so the radical 2 over 4 data from 0 to 2 pi is a radical 2 over 4 times 2 pi. You simplify it, that give you what? Pi radical 2 over 2. So that give you the surface integral, and you get the result. Okay, it's a nice procedure if you keep it in order. Is nothing to worry about. Just think about that integral that you start with is x squared ds. It's like a substitution method that you did before. Really, your x squared is over the given surface, so you have to change it. And that ds that you have is like that was differential of the arc length when you did the line integral. It's going to be differential of a surface area when you do the surface integral. And differential of a surface area is going to be the same as the norm of the normal vector. So you get this, that one too. You put them together. Okay, so this is going to be one case. Any question? So if you let me do one more for you in three-dimensional, one famous one. And so the one that I did, the situation was that the function was, okay, the surface. The surface was in terms of the x and the y, and you were able easily to find the normal vector, because your challenge is that normal vector. But sometimes the surface would be different, okay? And this is the famous one, is a sphere. So let's give you this one. We have a couple of nice one on the review that we're going to do it. So let's evaluate this integral. Evaluate the double integral on the surface integral on the x squared plus y squared plus z squared and the ds. Okay, that's going to be the case. Now, what's the surface? When the surface is the following. Surface S is given by, this is the information that you have, is given by x squared plus y squared. Okay, it's going to be x squared plus y squared equal to 9, a circle. Then x is between 0 and 3. And the y is between 0 and 3. And the z is between 0 and 9. Okay, so as you can see, the surface is a cylinder. A surface is going to be a cylinder because they give you the z here to know that. It's going to be a cylinder, so if you want to do it, you have to get the parametric equation of your parametric equation of your surface. And in this case, the parametric equation, of course, is going to be what? Is going to be cylindrical coordinate to get this one. Okay, so that's it. It may be given you as a sphere or maybe given you as a cylinder. Okay, and in two-dimensional, you see, if you drop it in two-dimensional, this is what you have. In two-dimensional is going to be the radius 3, 1, 2, 3, 1, 2, 3. Okay, and that's going to be 1, 2, 3, and then 1, 2, 3. So this is going to be, it's going to be a circle, but there is a restriction here because they consider the x and the y, everything is positive. So you don't need the bottom one. So this is going to be kind of a semicircle. This is a semicircle. This is a -3. And this is going to be 3, and this is 3. and this is 0. So you are interested between 0 and 3. That's a 0 and 3. You see, in two-dimensional, that would be the domain that you're going to apply. Okay, this is going to be the case. In the, in 2 dimensions, it's going to be polar coordinates. In the polar coordinate, this restriction is R is between 0 and 3, and your data is going to be between 0 and pi half. Okay, now you start with the fact that the cylinder is the surface. Okay, S is the cylinder, the surface is a cylinder. So you need a parametric equation with parametric, parametric equation. So the parametric equation, remember, is we talk about it, R of data and Z is equal to, the first part is R cosine of the data. I write it down and then I simplify it for you. It's going to be R cosine of the data, R sine of the data, and the fixed Z. But R is equal to 3. So your parametric equation is R of the data and Z is equal to cosine of the data, sine of the data, and Z. What's the domain? The domain is data is between 0 and pi half, and the Z is between 0 and 9. That's your domain. Okay, now you have a parametric equation. You have to go and find the normal vector for this one. Okay, and so what is going to be the normal vector? So the normal vector for, in terms of the data and Z, this is the one that's missing. So you remember it's going to be R of the data cross R of the Z, normal vector, because you need this normal vector to get it inside the integral, remember? So we have to go and find it. R of data, differential respect to the data. Differential respect to the data is going to be negative sine t, cosine t, 0. Integrate respect to the z, there is no z here, and the lift of z is 1. Okay, so get the cross product. So R of data cross R of Z is going to be the determinant of the matrix. You get the I, J, K. The first part is a negative sine data, cosine data, 0. And the second part, 0, 0, 1. Quickly find it. It's going to be equal to the I times. Cross out the first row, first column. The result, cosine of the data, minus 0, minus J times. Eliminate the first row, second column. Negative sine of the data, minus 0, plus K times K. Eliminate these two and you get nothing. It's going to be 0, minus 0, 0, minus 0. So your normal vector, R data cross RZ, is going to be equal to what? Is equal to the cosine of the data times I plus sine of the data times times J. So that gives you the normal vector. You need the norm of the normal vector. Okay, that's going to be the n of the data Z. So the norm of the normal vector n of the data Z is going to be equal to a square root of, I missed something. Sorry, R was equal to 3. Okay, I missed the 3 here. There is a 3 all over the places. So there's going to be 3 here. So I can factor it out eventually. Okay, there is a 3 here. Okay, and nothing here. So it's going to be 3, 3, 3. It's going to be 3, 3. And then we get a 3 here, and we get a 3 here. So when we get the square root, it's going to be 9 cosine square of the data plus 9 sine square of the data. You know that you take out the 9 as a factor, so the result would be radical 9, which is equal to 3. So the norm of that vector, most of the time is a constant, is equal to 3. You see, that's the extra thing that you have when you integrate it to get this function. Okay, now we are ready to go to the double integral. You replace that d of s by this, and then you change function to the r and the theta, and then you just do it. Okay, so let's go to the original format. This is it. So what do you want? The double integral, surface integral. Surface integral of x squared plus y squared plus z squared ds. So according to our formula, this is going to be a double integral on the domain. I'll just repeat the formula for you. It's going to be f of, okay, f of r of data z, okay, times the normal vector, n of data and z, and in this case, it's going to be dz d data. Okay, so we have to change this function into the format that you have for your x, y, z, and then start integrating. So the function that you have, you see the function f x, y, z is x squared plus y squared plus z squared. And you know that the x squared plus y squared is 9 because of the circle. So your function is simply f of x, y, z is equal to 9 plus z squared. Okay, 9 plus z squared. So go back and substitute here. Okay, so the integral is going to be the double integral. Sorry, that's the surface integral. The surface integral of x squared plus y squared plus z squared ds is going to be equal to the double integral. Now this is going to be 9 plus z squared. The normal vector, the norm of the normal vector is equal to 3. Then integrate respect to the z and the data. Okay, on the domain D. So we can pull out that so this is going to be 3, the double integral. Now, the domain that you have, the restriction for the z is 0 to 9. Okay, restriction for the data is 0 to pi half. Pi half. Remember, we talked about it. This is the quarter of a circle that you have. And the z was between 0 and 9. So this is it, 9 plus z squared dz d data. Now integrate respect to the z, which is easy integral to apply. Respect to the z, that given 9z plus z cubed over 3. Then z going from 0 to 9. And when you're done, you come back and you integrate respect to the data. So this is going to be equal to the 3 integral from 0 to pi half. Okay, 9, you substitute the 9 times 9 plus 9 cubed over 3, then the d data. Okay, you can simplify that, give you 81, and this would be 243. Okay, divide by 3 if you simplify everything. So it is going to be 3, 0 to pi half. That gives 324, the data. Okay, so it's going to be, that's it. You pull this one out. and then you take care of it, or it's going to be 3 times 3 to 4, and the integral would be data from 0 to pi half. And if you substitute 3 times 324 times the pi half, so you simplify it, 486 pi is going to be the final answer. This is true version of the surface integral. The version that the function is given to you in xy coordinate, the version that the function is given to you, in parametric form. And that's going to be the one. Okay, so we are almost done, but you have one extension to do. We did it for the scalar valued function. So how about if you be given a vector field? Everything would be the same, unless, these product are going to be just dot product. So we leave it here. We are not going to question you from this on this quiz, but I will finish it on Monday, and I start reviewing the final review. We don't have anything else, okay? And we are set on time, really, to get through this one. We talk about the Stokes theorem briefly because we don't have time, but we don't miss anything, so you have a good idea in case you want to study this one further in future. Okay, so have a good one. So practice quiz number 4 tomorrow. And just if you have done your tests, I will collect the test tomorrow. Then I will grade them and let you know. Okay, bye-bye. Have a good one. Thank you.